In this video, I'm going to talk about section 3.6, dealing with derivatives as rates of change. And mainly in this section, we'll look at how position, velocity, and acceleration are related to derivatives. Also, we're going to be finding functions for velocity and acceleration given the position functions. And also, we're going to be solving business application problems that are related to derivatives as rates of change. Mainly, we'll be looking at things like finding the average cost and the marginal cost functions, and then we'll be determining the average and the marginal cost at a given X value, and also how to interpret what a average cost and marginal cost are in words. So here, what we're going to be looking at is just some of the applications of this idea and demonstrate why calculus is called the mathematics of change. So let's start with position and velocity. Let's say we have an object moving along a straight line like this, and its location at time t is given by the position function s equal to f of t. All positions are measured relative to a reference point, which is often the origin at s is equal to 0, as you can see here. Here's s is equal to 0. Now, the displacement, by definition of an object between t equaling to a and t equaling to a plus delta t, is the change in s, or delta s. So that's your displacement. So let's say here's s equaling to f of a, and then you have s equaling to f of, and we go a little bit further out, that would be a plus the change in t. So s will be equal to f of a plus delta t. By the way, that's the Greek letter for delta, meaning the change in whatever your variable is. In this case, it's going to be the change in t, and t is going to be your time. So if I do a plus delta t minus f of minus a, that would be a. Actually, delta t, which is your change in time. And then your displacement here would be delta s, okay? Which is going to be f of a plus delta t minus f of a. All right, now let's look at a definition, or a couple of definitions, I should say, of average and instantaneous velocities. We should be familiar with those two formulas here. Well, they're written in a different way, but they're actually basically the same. So average velocity would be v sub a v, and then you have your instantaneous velocity. So if we let s equaling to f of t be the position function of an object moving along a line, the average velocity of the object over the time interval, which is going to be from a to a plus delta t, is the slope of the secant line between a and f of a, and a plus delta t, comma, f of a plus delta t would be this. F of a plus delta t minus f of a, all divided by delta t. Because this is y2 minus y1 divided by x2 minus x1. You'll end up with this. Okay, that's similar to an average velocity function that was talked about back in chapter 2. Now for the instantaneous velocity, that function, this is pretty much similar to the definition of a derivative. Okay, the instantaneous velocity at A is the slope of the line tangent to the position curve, which is the derivative of the position function. So here we got v of A is equal to the limit as delta t approaches 0 of f of a plus delta t minus f of a, all divided by delta t. When we're dealing with instantaneous, you're going to be taking the limit as delta t approaches 0 in this case. That would be similar to f prime of a, taking the first derivative. And we all should be familiar with this. It was written like the limit as h approaches 0. F of a plus h minus f of a all divided by h. This time, they're using the Greek letters. In this case, with respect to time, it'll be delta t, or the change in time. All right, let's talk about speed and acceleration. When you're only dealing with the magnitude of the velocity, we use the word speed. And speed, of course, will be the absolute value of your velocity. The absolute value, okay? And that's only when we're dealing with the magnitude of the velocity. Now for acceleration, that would be the rate of change of the velocity. And we define the acceleration in mathematics as the derivative of the velocity function with respect to time. So think about this. If we have a position function, your first derivative will be your velocity function with respect to time. Acceleration, we take the derivative of your velocity function with respect to time. So on the next page, you're going to see for velocity, speed, and acceleration. Suppose an object moves along a line with a position s equaling to f of t. Then the velocity at time t would be the derivative of your position function, ds dt, or f prime of t. And speed, of course, will be the absolute value of what f prime of t is. Absolute value of your velocity function would be your speed. And then the acceleration is going to be the derivative of your velocity function, which is also the second derivative of your position function, which we can write as f double prime of t. Okay, so keep that in mind, okay, because you're going to be using this when we do some of these examples on this video and in the homework in my math lab. So let's go ahead and start with example number 1. And here it is. Let's suppose the position of an object moving horizontally after t seconds is given by the following function, s is equal to f of t, where s is measured in feet with s greater than 0, corresponding to positions right of the origin. All right, so let's say our function in this case is f of t is equal to 5t squared minus 6t, and we're dealing with an interval from 0 to 7, which is, of course, the closed interval, 0 to 7. All right. So in part A, we're going to graph the position function. All right, so my position function is this. So we're going to first graph that on a coordinate plane, but we're going to use our graphing calculator to do this. So I'll just say here, use a graphing calculator. All right, so here's my graphing calculator. Excuse me. So let me go to y equal 2 and clear all this stuff that's in y, in my y1, y2, and y3. So in y1, I'm going to enter what my f of t is going to be, 5t squared minus 6t. Now I'm going to treat the t's like x's here in this calculator. So I'm going to do 5, press the xt theta in for the x, and then x squared to square it, minus 6, and then x. I'm treating the t's like x's here. Now my interval is from 0 to 7 for my t values here. So I'm going to go to window. And in this case, I'm going to look at the possible answer choices that are in the homework. You'll get a choice of which graph fits the one that's on your calculated screen. So for the x min and x max, it'll be from 0 to 7. So x min will be 0, then x max will be 7, the x scale will be 1. Now for the y min and y max, I'm going to let y min be negative 100, go down to y max, and I'm going to let that be 300. The y scale, I'm going to let that be, let's say, 50. Okay. And then I'm going to press graph. And this is what the graph of f of t is equal to 5t squared minus 6t would look like. Now, I'm going to show you on another screen why I use those. Because if you look at your answer, the possible answer choices here, you're going to see that they're using pretty much a different y min and a y max. Same thing here. And I know it's opening upward because if you look at t squared, which is the highest exponent in that function, its coefficient is going to be positive. So that means the graph has to open upward. So as you can see, it's opening, you can see here it's opening upward. So that means here it would be this answer choice right here. Has to be that answer choice. Okay. So here we already graphed the position function on the graphing calculator. You just have to pick the one that best fits or is close to the one that's on your calculator as well. So that's part A right there. Now, part B is to find and graph the position, the velocity function. And we have to answer the question, when is the object stationary? When does the object move to the right? And when does the object move to the left? Okay, so in this case, we need to find v of t. That's the velocity function, which is, of course, f prime of t. So if f of t is going to be 5t squared minus 6t, the derivative of that would be, we bring the 2 down, multiply by 5, you get 10. Copy over the t to the 1 less power, minus 6t, its derivative will be 6. So that means that the velocity function will be 10t minus 6. Now, in this case, we need to find out when is the object. Oh, also, we need to, before we do that, we need to find the graph of that velocity function. So here's where our graphing calculator comes in. All right, so I'm going to go to y equal to, I'm going to turn off this equation in y1 by positioning the cursor on top of that equal sign and press enter. So it will not be included when I graph it. Then go down to y2 and type in my velocity function, 10t minus 6. So I'm going to say 10, get the x for your 10x minus 6. Then I'm going to go to window. All right, my x min and x max will be from 0 to 7. I'm going to leave that alone, but I'm going to change the x min, the y min, and the y max. Let's see, the y min would be, let's say from negative 40, start at negative 40. Y max will be positive 40. Increment, or the y scale, would be 20. Okay, then press graph. And that's what the graph looks like. Okay, so we know it's crossing this x-axis at some point. Now, that's where the object will be stationary, meaning at what value of t will f prime of t be 0? That means the velocity will have to be 0 at what value? And v of t was 10t minus 6. That's going to be set equal to 0. Now here we can solve this equation for x. So if I add 6 to both sides, I'm going to get 10t is equal to 6. Divide by 10. This will be t is equal to, well, 6 over 10 reduces to 3/5. So that means 3/5, which is where this line or that velocity function, that's where it's going to be 0 because it's crossing the x-axis at 3/5. So that's where it's going to be stationary. Now, what about moving to the right? Well, it's going to be moving to the right. That means that v of t will have to be greater than 0. Okay. So that means 10t minus 6 will have to be greater than 0. And then if I get 10t by itself, that means 10t is greater than 6. That would mean t is greater than 6 over 10, which reduces to 3/5. So that means if it's greater than 3/5, if your t is greater than 3/5, it's going to be moving to the right. And it shows right here because 3/5 is at where this line is crossing the x-axis. So if it's greater than that, it's going to be moving to the right. Moving to the left will have to be, of course, taking v of t to be less than 0. So again, we do 10t minus 6 is less than 0. That would mean 10t is less than 6. T is less than 6 over 10, which is again less than 3/5. And it shows here in this graph right here. Okay, if I can show it right here. So here's 3/5. So if it's moving to the left, it's going to be where t is less than 3/5. So the intervals that they want, well, we know it's going to be stationary, meaning it's not moving. Stationary at t equals 3/5. Moving to the right. Now we have to pay close attention to this interval right here. We're restricted from 0 to 7. So if it's moving to the right, it's got to be greater than 3/5. So we use a left parentheses for 3/5. And we go up to the maximum on this interval, which is going to be 7. So from 3/5 to 7, the object is moving to the right. And then moving to the left, now keep in mind, we're restricted from 0 up to where it's stationary at, 3/5. And we use a right parentheses because we don't want to include 3/5. So the object is stationary at t equal 3/5. The object is moving to the right from 3/5 up to positive 7 and moving to the left from 0 to 3/5 because we're only restricted on this interval from 0 to 7. Okay. So that is part B. Finding out when the object is stationary, when it's moving to the right and moving to the left. All right, now part C is determine the velocity and acceleration of the object at t is equal to 1. Okay, let's see what's going on here with this one. All right, I need the velocity at t is equal to 1. Well, I already know what the velocity function is going to be, which is v of t, that's equal to 10t minus 6. So that means here, t is equal to 1, so v of 1 would be just simply replacing the t with 1. So it'd be 10 times 1 minus 6. 10 times 1 will be 10. 10 minus 6 will be 4. So my velocity of this object at t is equal to 1 would be 4. And since we're dealing with feet and in seconds, it has to be written as this rate, 4 feet per second. 4 feet per second. And also, we need to determine the acceleration of the object at t is equal to 1. So let's find the acceleration at t equaling to 1. Well, we know what the velocity function is. V of t, that's going to be 10t minus 6. However, we need the acceleration. The acceleration, of course, is the derivative of our velocity function, which is, of course, v prime of t. So if we take the derivative of 10t minus 6, that's just going to give us 10. So our acceleration function would be just 10. So at t is equal to 1, a of 1 would just simply be 10. And it'll be 10 feet per square second. Okay? It's going to be that length per square unit of time. Okay? So it's going to be 10 feet per second square. Now for part D, when the velocity is 0, we need to find out what the acceleration of the object is going to be. So I'm going to do part D over here. So here, when your acceleration v of t is equal to 0, well, we found the derivative of our acceleration, which is going to be 10. So a of t, that's of course just going to be 10 feet per second square. Okay. So that one was quite easy because we're pretty much told we got the acceleration. So the acceleration is just pretty much going to be a number. All right, now part E. On what intervals is the speed increasing? Now keep in mind, when we talk about speed, we're talking about the absolute value of the velocity function. So here, in this case, absolute value of v, which is the velocity, that's equal to the absolute value of the first derivative, f prime of t. And that first derivative we found out was 10t minus 6. So in this case, we have the absolute value of 10t minus 6. Okay, now what I'm going to do here is graph this on my calculator. So I'm going to go to y equal 2, and I'll go ahead and put the cursor on above that equal sign, on top of the equal sign, and just hit enter to not include that. Now to enter the absolute value of 10t minus 6, I'm going to do this, press the math key, and I'm going to go under the number menu and select ABS for absolute value, and it will give you the two absolute value bars. And I'm going to enter 10t minus 6 as 10x minus 6. Use my right arrow key to get out of it. What I think I need to do here is, if I can, I'll go ahead and do the graph and see what happens. Okay. And as you can see here, in this case, we want to find out, in this case, on what intervals is the speed increasing. That means it's going up, increasing, going up. So from 3/5, which is that point here where the velocity function crosses the y-axis. So from 3/5 on up to our highest y value, the highest x value on the interval, which is going to be 7 because we're restricted to 0 to 7. So in this case here, the speed is increasing on the interval from 3/5 up to 7, okay? Because the interval is restricted from 0 to 7, but from 0 to 3/5 is just decreasing. After 3/5 is going up, it's increasing, okay? So that's how we do example 1, okay? Now let's take a look at another example. Let's say we had a function like this. Suppose the position of an object moving horizontally after t seconds is given by the function s is equal to f of t, where s is measured in feet with s greater than 0 corresponding to positions right of the origin. So pretty much these directions are the same here. Our function is a little bit different. We got f of t is equal to t cubed minus 15t squared plus 72t. The interval this time is from 0 to 8 for our time. So let's start with graphing the position function. So I'm just going to say graphing calculator. It'd be best to use that because they're going to give you a choice of graphs that you will use in order to determine which one is the best fit for the one that's on your screen. So I'm going to go to y equal to, excuse me. So in this case here, I have f of t is equal to, the t's will be treated like x's, so the x, and then use your hat key and then type in the number 3 for the x cube minus 15, get your x and then square it, plus 72x. Now I'm going to use my window to change some things here. X min is still going to be 0, but X max will be changed to 8. X scale stays at 1. Now for Y min, I'm going to let my Y min be 0 and Y max will be 160. The Y scale, it's going to be 20. So the Y scale will be 20. And then we press the graph key. And this is what the graph of that function looks like on that interval. So again, when I come back to this right here, you just have to look at the graph and compare that to these answer choices for the graph that closely fits the one that you got on your calculator. Okay, and more than likely it's going to be this one right here. Okay, that would be the graph of the position function. Okay, so that's part A. And now part B is to find and graph the velocity function. Find and graph the velocity function. So your velocity function v of t is going to be the derivative of f of t. So that means here, if we take the derivative of t cubed minus 15t squared plus 72t, we're going to end up with 3t squared minus 30t plus 72. That's our derivative of the position function, which is going to be our velocity function, by the way. And then we're going to ask ourselves, when is the object stationary? When is it moving to the right? And when it's moving to the left? Okay. All right, so here's what we're going to need to do right here. Let's find out where it's stationary. That means we take our function and set that equal to 0. And our VOT function is going to be 3t squared minus 30t plus 72. And that's set equal to 0. Now we need to find out what t is going to be. And in this case, we need to do some factoring on the left-hand side. So that means here, if I factor out the 3, I'll have t squared minus 10t plus 24. Because the common factor here is 3 in all 3 of those terms. Now I can factor the trinomial inside the parentheses at t squared minus 10t plus 24. So I'll bring down the 3. This can be factored into 2 binomials. T squared breaks up as t and t. The middle term is a minus, the last term is a plus, so they both have to be minus. Factors of 24 that would give me 10t would be 4 and 6. Factor completely, that would be 3 times t minus 4 times t minus 6, equaling to 0. And then we set each factor equal to 0. So the 3 will be equal to 0. T minus 4 would be equal to 0. And t minus 6 equal to 0. Well, 3 cannot be equal to 0, so we can cross that out. T minus 4 equal to 0 would mean that t is equal to 4. And t minus 6 is equal to 0 would mean that t is equal to 6. So t equal to 4 and t is equal to 6 where the object is stationary at those 2 values here. Okay, let me go ahead and graph this velocity function. So I'm going to go to y equal to, I'm going to turn off this equation. And in y2, I will type in 3x squared minus 30x plus 72. Now let me go to window, because I'm going to find out what type of window I'm going to need to use here. From 0 to 8, the x min and x max will remain the same. Let's see, but for y min, I'm going to change that to negative, I'm going to say negative 40. And then y max will be 80. The y scale will remain as 20. And now I'm going to press graph. And you can take a good look and see where at 4, 1, 2, 3, 4, this curve is crossing the graph at 4 and is crossing the graph again at 6. Okay, so now we want to know where is it stationary and where is it moving to the left and moving to the right. Well, at 4, the curve is crossing the x-axis at 4 and at 6. So those are the 2 points where it is stationary, or the object is stationary. So it's going to be stationary at t is equal to 4 and t is equal to 6. Now, we need to pick the intervals where it is moving to the right. In other words, where is this graph positive if it's moving to the right? Let's look at this graph. So that means it's above the x-axis. So from 0 up to 4 is positive, it's above the x-axis. So from 0 to 4, it's moving to the right. So from 0 to 4, and we do not include 4 because it's stationary at 4. So as you can see, this graph is positive. But between 0 and 6, notice that the curve is below the x-axis. That means that object is moving to the left. So I'll say moving to the left, and that's between 4 and 6. Those endpoints in this case are not included because at 4 and at 6, the object is stationary. And then after 6, it goes back above the x-axis. So that means that this graph or the object is moving to the right from 6 up to 8, because our restriction is from 0 to 8. So that's the other part of that answer there. Okay. And also you'll be given graphs to select to determine which one best fits the one that is on your calculator. And pretty much it'd be best that you use the restrictions that they have for the X and the Y coordinates. And I'll show you again on another screen, which is right here. So it'll be this one right here, I'm sure. Okay. Because as you can see here, they use from 0 to 8 for the X and then from -40 to 80 in increments of 20 for their Y-axis. Okay, so all of that was part B. Now part C. Determine the velocity and acceleration of the object at t equaling to 1. All right, so let's find the velocity at t is equal to 1. And I'm going to write down what that velocity function was, which was still f prime of t. And that was 3t squared minus 30t plus 72. So the velocity at t equaling to 1, we just simply substitute our t with 1. So it'll be 3 times 1 squared minus 30 times 1 plus 72. Simplify this. 1 squared will be 1 times the 3 in front would be 3 minus 30 times 1, which is 30 plus 72. 3 minus 30 will be -27. -27 plus 72 would be 45. And this will be in feet per second because it is velocity. Velocity is always going to be some unit of length per unit of time. Okay. Now, what about the acceleration of an object at t equals to 1? Well, we know what v of t is. That's this. Now to find a of t, that's just taking the derivative of our velocity function. So if this is my derivative of the position function, which is the velocity function, take the derivative of that, that would be 6t minus 30. 6t minus 30. Now, let's find out what that acceleration would be at t is equal to 1. We just substitute the t with 1. You'll get 6 times 1 minus 30. 6 times 1 is 6. 6 minus 30 would be -24. And our acceleration is going to be feet per square seconds. So the acceleration at t is equal to 1 would be -24 feet per square second. Excuse me. All right, part D. Determine the acceleration of the object when its velocity is 0. So at v of t equaling to 0, so when the velocity was 0, okay, at the velocity being 0, that means in this case, our t values were 4 and at 6. Our t values were at 4 and at 6. Now, in this case, we'll just have to find out what the acceleration will be at t is equal to 4 and at 6. So at t is equal to 4, the acceleration there would be, we just take our acceleration formula or expression, which is 6t is equal, which equals 6t minus 30, substitute the t in with 4. So it'll be 6 times 4 minus 30. That's going to be 24 minus 30, which will be -6. And that's going to be in feet per second squared. So this is for t is equal to 4. Now for t is equal to 6, this time a of 6 will be 6 times t, which is 6, minus 30. 6 times 6 will be 36. 36 minus 30 would be 6. So it'd be positive 6 feet per square second. Okay. So in this case here, the acceleration for each time at t is equal to 4, your acceleration will be -6 feet per second squared, and at t is equal to +6, it'll be +6 feet per second squared. Because we came up with 2 values for t, one at 4 and the other one is at 6. Now for part E. And in part E, it says on what intervals is the speed increasing? All right, if you remember, speed is always going to be the absolute value of our velocity function. So that's the absolute value of f prime of t, which is the velocity function. And that velocity function, of course, was the f was 3t minus 30t plus 72. And that right there is the absolute value function. So I'm going to put this in the calculator. So I'm going to go to y equal to, I'm going to turn this equation in y2 off and enter this. The t's will be treated as x's, so it'll be 3 xt theta for the x, and then we square it, minus 30 x plus 72. Hit graph. Oh, I'm so sorry. I forgot to do something here. Let me clear this out. I forgot to put absolute value here. So to do that, let me press the math key and then go to fraction, go to the number menu and select number 1 for absolute value. Then I will put this in the calculator. So it'll be 3x and then squared minus 30 and then x plus 72. And then we'll go ahead and press graph. Here's what the graph looks like. Now notice for this, on which intervals is the speed increasing? If you notice here, starting at 4, it starts to increase. So here from 4 up to, and I'm going to say 5. So from 4 to 5, it's increasing. And actually, I cannot use brackets. I need to use parentheses. So between 4 and 5 is increasing. Okay, because after 5, it starts decreasing when you get down to 6. And then from 6 on out, it starts to increase. So from 6 up to the limit of 8, that's when the graph is increasing, or the speed is increasing between 4 and 5, and between 6 and 8, where 8 is included. Okay. Right, so that's how we do example 2. All right, now let's talk about average and marginal cost used in economics and business. Okay, so that's the next thing we'll look at in this section. All right, so let's talk about the cost function. The cost function, which is going to be C of X, gives the cost to produce the first X items in a manufacturing process. So you'll be given a cost function. To find the average cost to produce X items, it is going to be C bar of X equaling to C of X divided by X. So you'll take your cost function divided by X to get the average cost to produce X items. Now the marginal cost, which is going to be the derivative of your cost function, or C prime of X, that's going to be the approximate cost to produce one additional item after producing X number of items. So let's say you already produced 200 items. To find the marginal cost, you want the approximate cost to produce the 201st item after 200 items were produced. Okay, so now let's apply that to example 3. It says to consider the cost function C of X is equal to 1500 plus 0.08x. And here the interval is X is between 0 and 5,000 inclusive, and A is 2,900. So as you can see, the value of 2,900 will be between 0 and 5,000. And here I want to find the average cost and marginal cost functions. Determine the average and marginal cost when X is equal to A. Interpret the values obtained in part B. All right, so in this case here, let's look at part A, finding the average cost and then the marginal cost. Of course, the average cost, the way you find that would be C bar of X. That would be your cost function divided by X. So the cost function was 1500 plus 0.8x. All that's divided by X. Now what we can do is write that as 1500 divided by X plus 0.8x divided by X. Just break each one of those apart. So 1500 divided by X would just be 1500 over X. But 0.8x divided by X, here the X is divided out. You'll be left with 0.8. So the average cost function there would be 1500x plus 0.8. And now we want the marginal cost function. Marginal cost function. That's taking the derivative of your cost function right here. Well, we take the derivative of each piece. So the derivative of 1500 is 0. The derivative of 0.8x will be just simply 0.8. That's all there is to that problem. That's part A, finding the average cost and the marginal cost functions. Part B, And in this case here, we want to determine the average and marginal cost when X is equal to A. Determine the average and marginal cost when X is equal to A. Well, we know, let's say X is equal to A, and A is 2,900. So that means just substitute the A with 2,900. So that means X is equal to 2,900. So now we can find the average cost. Our average cost was this right here, C bar of X. That was equal to 1,500 over X. Well, let's substitute that X with 2,900. Well, let's go ahead and rewrite the whole function. 1,500 divided by X plus 0.8. And then let's do our substitution. C bar of X, which is 2,900. That would be 1,500 divided by 2,900 plus 0.8. And I'll go ahead and show this to you on the calculator. So it'll be 1,500 divided by 2,900 plus 0.8. Now, if we were to round that off to 2 decimal places, since we're dealing with money amounts here, this will be 1.32. So the average cost would be $1.32 based on that cost function. So the average cost would be $1.32 for producing, let's say, 2,900 items. And then the other part is the marginal cost when X is equal to A. So to find the marginal cost, that's of course C prime of X, which is of course 0.8 from here from part A. So the marginal cost of C prime of X, which is 2,900, that's not going to matter. It's just going to be 0.8. Or in this case, let's say we want to write that in dollars and cents, 80 cents. That would be the marginal cost. So that's part B. Now we're going to use part B to interpret the values that we got. So that means here, what does those values mean? What does the average cost and the marginal cost mean? Let's start with the average cost. What that means here is this: the average cost is $1.32 when 2,900 items are produced. So when you produce 2,900 items, $1.32 would be the average cost. Now, what about the marginal cost? How can we interpret that? Well, let's say this, that the cost of producing. Now, keep in mind that the marginal cost is going to be the approximate cost to produce one additional item. After 2,900 items have been produced, the one extra would be 2,901. So after producing the 2,900 first item, the cost of producing that would be 80 cents. Okay. That 80 cents represents the cost of producing one additional item after 2,900 items have been produced. Okay. Okay, here's another example of this. All right, let's say we want to consider the cost function C of X is equal to 0.03x cubed plus 0.6x squared plus 40x plus 90. And here, X is between 0 and 1500, and A is going to be 500, which is between 0 and 1500. So here we're going to find the average cost and marginal cost functions, determine the average and marginal cost when X is equal to A, and interpret the values obtained in part B. So let's find out what the average cost function will be first, and the marginal cost function as well. All right, so keep in mind, C bar of X is always going to be the cost function divided by X. So this will be, the cost function is 0.03 X cubed plus 0.6X squared plus 40X plus 90. That whole thing is divided by X. Each term in the numerator will be divided by X. So you have to think about this, 0.03 X cubed divided by X. One of the X's divides out, you'll be left with an X squared here. So it'll be 0.03 X squared. Then 0.6X squared divided by X. Again, one of the X's will divide out, you'll be left with an X in the numerator. So it will be 0.6X plus, and I left off the X, so I need to add that, 0.6X, 40X divided by X. Well, the X divide out, you'll be left with a 40, then 90 divided by X will be 90 over X. So this is your average cost function, 0.03X squared plus 0.6X plus 40 plus 90 over X. So that's part A. Now for the marginal cost. We take the derivative of our cost function. So this function right here, we just take its derivative. So the derivative of 0.03 X cubed, this will be 0.09 X squared. 3 times 0.03 will be 0.09. Copy of the X to the 1 less power would be X squared. Plus 0.6X squared, its derivative will be 1.2X. Plus the derivative of 40X will be 40. The derivative of 90 is 0. So the marginal cost function, C prime of X, would be 0.09X squared plus 1.2X plus 40. So that represents part A. Part B is determine the average and marginal cost when X is equal to A. Well, in this case, your A was 500. So I'll just replace that A with 500. That is what X will be, 500. So now to find the average cost, we do this. We just take C bar of X, which is 500. We use this formula for C bar of X, just substitute the X with 500. So we're going to have 0.03 times 500, and that's going to be squared, plus 0.6 times X, which is 500, plus 40, plus 90 over X, which is 500. And I believe I can type all of this in the calculator to get the average cost. And that is what I will do. So here I got 0.03 times 500, and that's going to be squared, plus 0.6 times 500, plus 40, plus, and I'm going to put the 90 divided by 500 in parentheses, and then hit enter. And this will be my answer to 2 decimal places. $7,840.18. $7,840.18. That would be the average cost for producing 500 items. Now the marginal cost. So this is C prime of 500. I'm using the first derivative here, and I'm going to substitute each x with 500. So C prime of 500 would be 0.09 times x, which is 500, and that's squared, plus 1.2 times x, which is 500, plus 40. So in this case here, 0.09 times 500, that's squared, not minus, plus 1.2 times 500, plus 40. And I get $23,140. So that means the marginal cost would be $23,140. Now, in part C, we're to interpret those values that we got in part B. So let's interpret the average cost. So what that means here is this: if we're dealing with 500 items, when 500 items are produced, the average cost is $7,840.18. Now let's interpret the marginal cost, which is this: the cost of producing, and keep in mind the definition of a marginal cost is the cost of producing one additional item after, in this case, 500 items were produced. So for the 501st item, that cost would be $23,140. That would be the marginal cost. Okay. All right, and finally, there's an example 5. There's this. We're going to let C of x represent the cost of producing x items, and P of x be the sale price per item if x items are sold. The profit, which is capital P of x of selling x items, is capital P of x is equal to x times lowercase p of x minus C of x. That's revenue minus cost. The average cost, the average profit per item when x items are sold is going to be P of x divided by x, and the marginal profit is going to be dP dx. The marginal profit approximates profit obtained by selling one more item, given that x items have already been sold. Consider the following cost functions and price functions. Complete parts A through D below. Here's your cost function. Capital C of x is equal to negative 0.4x squared plus 50x plus 120 divided by P of x is equal to 300. I'm sorry, not divided by. Also, the profit, your price function. P of x is equal to 300 and A is equal to 500. Let's find the profit function P of x. Now, of course, that profit function is given to you. P of x is equal to x times P of x minus C of x. Now I'm going to bring down the x. P of x was, in this case, 300 minus C of x. That's going to be that negative 0.04 x squared plus 50x plus 120. Now, if I simplify this, 300 times x is 300x. That minus sign is going to be distributed over everything in the parentheses, and it changes the sign. So the minus makes negative 0.04x squared plus 0.04x squared. The minus makes the 50x minus 50x. The minus makes the 120 minus 120. Now, if we simplify this by combining, combining like terms here, I'm going to pull the 0.04x squared out in front. 30x minus 50x will be plus 250x. And then bring over the minus 120. That would be your profit function there. 0.04x squared plus 250x minus 120. Now in part B, they want the average profit function and the marginal profit function. All right, so the average profit function is going to be P of X. Well, let me go and write that. Average profit function the average profit function is going to be P of X divided by X. Well, P of X is going to be that 0.04 x squared plus 250x minus 120. And all that's going to be divided by X. So we're going to take each term in the numerator and divide that by X. Well, one of these X's will divide out. So you're going to have 0.04x plus 250x divided by X. The X's divide out. You'll be left with a plus 250 minus 120 will be divided by X. That is what your average profit function will be. And I'm going to label this as P bar to show you that it is the average profit function. All right, now for the marginal profit function. Marginal profit function is this. Here we're going to do the derivative of that profit function with respect to X, since it's in terms of X. This is our marginal profit. This is our profit function here. Let's take the derivative of that. 0.04 x squared, its derivative will be, bring the 2 down, multiply by 0.04, it will be 0.08. Copy over the x to the 1 less power, plus the derivative of 250x will be just 250. And the derivative of minus 120 will be 0. So this is my marginal profit function, 0.08x plus 250. So I've answered part B. Now let's answer part C. Find the average profit and marginal profit if X equals A units have been sold. Well, A in this case is the 500. So that means X will be equal to 500 since X is equal to A. Now let's find the average profit. Using that average profit function that we have here, we just substitute the X with 500. So we're going to have 0.04 times X, which is 500, plus 250 minus 120 divided by X, which is 500. Using the calculator, 0.04 times 500 plus 250 minus, now I'm going to put the 120 divided by 500 in parentheses. So the average profit would be $269.76. Okay. And now for the marginal profit. We're going to use that marginal profit function of 0.08x plus 250. Substitute the x with 500. So it'd be 0.08 times 500 plus 250. And that will give us $290. So that means here, the marginal profit would be $290. And of course, in part D, they're going to want us to interpret the meaning of the values in part C. Interpret the average profit if X is equal to A units have been sold. Interpret the marginal profit if X equals A units have been sold. Well, let's start with the average profit. What does that mean? It means that the average profit when 500 items are sold is the $269.76. So after 500 items have been sold, your average profit will be $269.76. Now for the marginal profit, let's interpret that by using the definition of the marginal profit. The marginal profit obtained by selling, and of course, there's one additional item after 500 items are sold. So after selling, by selling the 500 first item, okay, the 500 first item, its marginal profit would be $290. So that's how we interpret the average profit and the marginal profit in this particular situation. Okay. Okay, allow me to go back to example number 1, especially with part D, because with that problem, you were told to determine the acceleration of the object when its velocity is 0. Now, when its velocity is 0, we figured this out. When that velocity was 0, that means that the time was 3/5. And actually, we were to find the acceleration at that time, 3/5. So A of 3/5, well, the acceleration when we did the second derivative, it came out to be 10 feet per second squared. So at 3/5, its acceleration would still be 10 feet per second squared. So the acceleration at 3/5, at time 3/5 of a second would be 10 feet per second squared. I just need to clarify that particular problem since you were wondering why A of t was 10 feet per second. And I need to clarify at when the velocity was 0, the time we came up with in part B was 3/5. And then we use that time to substitute into our velocity formula. I mean, acceleration formula. Okay, so that does conclude this video in section 3.6, dealing with derivatives as rate of change. Feel free to contact me if you have any questions about anything that's presented in this video or on anything in the homework on my math lab.